the Red Sea. And here we have a transcontinental split between Africa and Arabia that's occurred in the very recent geological past. And we know there's an active constructive margin down the axis of the Red Sea. Then this is the place to investigate the problem. What you notice straight away is the parallelism of the coastline. Note here in the north that the coastlines are straight, continuing the line of the Gulf of Suez. And then they start to zigzag, but together. Obviously, there's been a lot of transcurrent movement here in the Gulf of Aqaba, and we have problems of overlap here in the north, and even more so down here in the south. Geophysically, it is a typical piece of continental plate with some 35 kilometers of sealic crust. The crust, which we often call the basement, is not particularly old. It was formed sometime between 1200 and 500 million years ago. During the Phanerozoic, the last 540 million years, nothing much has happened. Look at this outcrop of basement and these scarps. This erosion surface was formed at near sea level, but it's since been raised by nearly 2 kilometers above sea level. The whole region has been updomed, mostly around here. And one possibility to explain the initial formation of the Red Sea is that this bulging of the crust caused stretching across the line of the Red Sea and the development of a trough or graben. Or perhaps the two plates moved apart before the uplift happened.
During the last 20 million years, this area has certainly been one of considerable instability. But prior to that, for 500 million years, this was a very stable area. During that period of stability, terrestrial sediments were deposited over the whole of the area. These terrestrial sediments were interbedded with marine and intertidal sediments, which were the result of transgressions coming up from the north in this direction here. These terrestrial sediments are very similar to the millstone grit in Britain. Unlike the millstone grit, they are a facies deposit. That is, they vary in age from place to place. These deposits are called the Nubian and were laid down in large, flat, depositional sheets of fairly coarse sediment. And similar deposits can be found as far east as Jordan. Just look at these structures, which can be found throughout these deposits. Detailed mapping of them showed that they're deposits of a large braided river. These conditions must have lasted a long time, because these similar sediments are known to be lower Paleozoic in age. So we're sure that rivers must have been draining this area here for hundreds of millions of years. During the lower Cretaceous, a marine transgression covered the whole of this area here. We find shale deposits. The best exposed outcrop is found at Crocea, and these shales, with plant remains, are interbedded with shallow water limestones rich in oysters. These rocks are a mixture of chalks and blyclastic limestones, and in the past these limestones have proved to be quite a durable building stone. Up to the Middle Eocene, 45 million years ago, it's important to remember that none of these deposits showed any change in facies. Coarse conglomerates like this are found throughout much of the Red Sea area. Difficult to date them, but fossils have been found in marine sediments above and associated with the conglomerates. These Piedmont fans were formed as a result of uplift of the margins of the incipient Red Sea along here. And this is the first sedimentary evidence of anything strange happening in this area. The flanks continued to rise, and a marine trough formed in between, open to the north, but closed to the south. This is the section, and unlike the rest of the Red Sea, the Gulf of Suez is a graben, and you can clearly see the marginal faults in the cross-section. The section from top to bottom represents about 4,000 meters. During high stands of sea level in the Miocene, conglomerate fans and shallow water reefs were being formed along the margins of the Red Sea, and in deeper water, shales containing planktonic organisms were being deposited. All these features indicate a sea of normal salinity. For a number of reasons, the Red Sea must have been cut off at some time. As the sea became isolated, evaporation caused sea level to fall. Salinity increased to about 10 times what it is normally, and halite was deposited. Each time this happened, a little less than 2 meters halite was laid down. But we find thin shale bands interbedded with the halite, so sea level must have risen again periodically. We know there's a total thickness of 5 kilometers of halite in the Red Sea basin at the present time. This means that the process of filling and evaporation must have been repeated nearly 300 times.
There is a minor complication, however, And it's this ridge of high ground. Surrounded by basaltic lava flows, a fragment of the African basement seems to have got torn off in the spreading process. And as it wasn't attached to Arabia, it was left behind, stranded as a fragment of crust. If we dispose of the AFAR triangle, the coastal fit is good. Movement must have occurred here, along the Aqaba transform. And this area, the Midian Peninsula, upsets the good coastal fit. This is obviously another complication.
The Gulf of Aqaba is relatively narrow, steep-sided, and quite deep. Locally it achieves depths of 16 to 1700 meters. Now, this line is a line of a major fault. And the Gemini astronauts were able to look along this fault, and fortunately they photographed it for us. Here we see the trend of the Gulf of Aqaba, and then you can trace the fault all the way up Wadi Araba to the Dead Sea, and it continues beyond. The line of the fault is quite clear there. Now the displacement on the fault is sinistral, that the rocks facing you have moved to the left. Here in the north, the fit is almost perfect, except for the small peninsula of Midian, which overlaps Africa. Although the peninsula mostly comprises late tertiary sediments, there are inliers of basement rocks, so it's partly at least continental crust, and it projects into the shield of Africa where there is no re-entrant to accommodate it. These rocks lie immediately adjacent to the Aqaba fault, and it's likely that they were originally parts of the Arabian shield, which became displaced during movement along the fault, so we can discount them in this fit. We know that a sinistral movement of 105 kilometers has occurred along the Aqaba Jordan Valley fault. The trouble is, such movement does not open the Red Sea to its present position. Something is obviously wrong. Perhaps our assumption of a tight coast-to-coast fit was in error. So let us start from a position about which we are certain, namely present-day geography. Move the Arabian plate 105 kilometers